Hi, this is Chen, and this is my Lab 5 on the motion of falling objects. The objective of this lab was to observe the motion of two objects that are dropped from rest, and to construct a computational model that included only the effect of gravity, and then another model for the effects of both gravity and drag. For my fast object, I used a ping pong ball, and for the slow object, I attached a parachute to the ping pong ball. The main result was that F net is equal to the force of gravity plus the drag force, and the models provide good predictions of observed motion.
Alright, so here's the video of the fast moving object, which is just a ping pong ball. I set the axis at the original position of the ball and the calibration stick as 4 centimeters for the diameter of the ball. If we play the video, you can see that the average location is the center of the ball each time, and the video lasts for about 0.367 seconds. So if we plug all this info into Python and run it with only the force of gravity acting on the ball, we get this. Notice the arrow. If we compare this in a spreadsheet with the tracker information, you can see that the Python model is just slightly off because there's no drag. So if we go back into the model and add the force of drag, then when we run it, we can see that the downward force is decreasing, as you can see from the arrow. If we take this new information and plug it into the spreadsheet, we can see that the Python and the tracker models are pretty much almost the same, except for the very last part where the ball hits the ground. Alright, so now we move on to the video of the slow moving object, which is just a ping pong ball with a parachute attached to it. The conditions are pretty much the same as the last video. Axis is set at the origin, and the calibration stick is still set at 4 centimeters, and the average location is still the center of the ball. So if we run this video, we can see a pretty big difference, and it lasts quite a bit longer at 0.5 seconds now. And if we plug this new information in the Python and run it with only the force of gravity acting on it, we get this. So if we plug this into the spreadsheet, we can see that there is a huge difference between the Python and tracker model because there's no drag included, and they look completely different. So now if we include the force of drag in our Python model on the slow object, we can see a pretty huge difference as soon as we start running it. The arrow goes away almost immediately, and if you look at the graph, you can see that the velocity is pretty much constant at this point. And if we go to the spreadsheet, we can see that our Python model and the tracker information are nearly identical now, and it's almost a perfect match. So what does this all mean? I've already briefly touched up on this subject, but basically if we look at the slow moving object and the models with drag and without drag, the model without drag looks completely different from the tracker information as opposed to with drag, where it's almost a perfect fit. So if we go back to the model again and run it one more time, we can see that the velocity is pretty much constant at the end, which indicates that the ball has already reached terminal velocity. Alright, so what if we consider the case where the slow moving object starts off with an initial velocity instead of starting at rest? Well, for the model without drag, if we give it an initial vector velocity of 0, -10, 0 and run it, we can see that there's a slight jump at the beginning, but if we look at the graph, it's still parabolic instead of linear, which indicates that it still doesn't reach a terminal velocity. Okay, so now if we include an initial velocity in the model with drag and run it, we can see that it starts off a little bit faster, and it also reaches terminal velocity faster. This is due to the fact that the drag force is equivalent to the velocity. Alright, so just to summarize, the main result that we got from this lab was that the net force acting on a falling object is equal to the force of gravity plus the drag force. And an object will reach terminal velocity once gravity and drag equal out. So that's pretty much it. Thanks for watching my video. Hope I didn't bore you to death with my monotone voice.